Yeah, today's talk is really going to be, forgive me for bloviating a bit, kind of an overview of some quantitative and philosophical ideas I have about sort of where the community ought to be going and where it is, that I've developed over the course of the last 10, 15 years, my whole career really. And that career has really been really a blessing for me. It's allowed me to go to some really unbelievable places, the CCA among them. I started my career in my hometown of Calgary, Alberta in Canada. Fun fact, that's also where Greg Bryan went to school for his undergrad. And I mean, you could see here, we're in the shadows of the Rocky Mountains. It's amazing, it's beautiful. I did my PhD, as was mentioned, at McMaster University in Hamilton, which is surrounded by this unbelievable wetland they call Cootes Paradise. And then I was able to go to Heidelberg and basically live in a fairy tale. And now I've been able to come to see not just what the best Canada has to offer, what the best Germany has to offer. I'm lucky enough to get to see what the best America has to offer in Memphis, Tennessee. This is our famous landmark, the Bass Pro Pyramid. And over the couple of years, going on towards decades now, unfortunately, that I've been thinking about these things and working on galaxy formation, it's really been centered around this one question, like, how do we understand how these things get to be the way they are? I think that anyone who works on anything would ultimately sum up that as being their focus. How does this stuff work? And I could, and I have in the past, given a talk that kind of starts out with, we don't understand any of this stuff. We don't know how galaxies form. And then I can go and show you all of my papers that explain everything. We're great, we understand everything. And then I'll tantalize you a little bit at the end with, actually, it's not as simple as we might thought. And I am going to do that today. So I'm spoiling my own talk here, but I think that there's more to this that's more subtle and in many ways much, much more interesting than this just linear path towards understanding or truth. So the picture that we start out with, that the community as a whole kind of started out with 50 or 60 years ago, is that gravity drives all of this. We start with perturbations from the CMB. Those perturbations collapse into dark matter halos, inside of which galaxies form. And in those galaxies, perturbations in the ISM collapse to form stars. And at the center of the galaxies, torques can drive stuff onto the supermassive black holes we see. And of course, everyone here knows this is not true. This is not the simple picture because it doesn't work. If we look, for example, at the abundances of galaxies, how many galaxies we see per cubic megaparsec compared to how many dark matter halos we ought to see from our collisionless simulations, we not only have too few dim galaxies, we also have too few massive or bright galaxies. So clearly there's something more than just a constant efficiency going on here. And more catastrophically, the sort of state of the field at the beginning of my PhD was essentially no one can make a realistic galaxy. Now, that's with a big, big, big asterisk, but generally galaxy simulations were forming too many stars if you look at the stellar mass to halo mass relation. And they were forming these stars in dense central bulges. We weren't forming disk galaxies, and we weren't forming disk galaxies with the right stellar mass fraction. If you look at the halos around galaxies, the number of satellites that were predicted for galaxies like the Milky Way were orders of magnitude higher than the number of satellites that we actually observed. Meanwhile, if you looked in clusters, more dense environments, the simulations and observations actually agreed quite well. So again, we have something going on here that's more than just a fudge factor. And if we look inside the satellites around the Milky Way at their own dynamics, kind of local group dwarfs, we have this issue where the rotation curves of those dwarfs seem to indicate they live in core dark matter halos, which was not the prediction of collisionless simulations. We predicted that you had this universal NFW profile with a steep cusped density profile. And I think the easiest of these problems to understand is really in many ways the most indicative as well, is this so-called missing baryons or missing metals problem. If you look at the baryon fraction within galaxies across many orders of magnitude, you find that there's essentially no galaxy that has the amount of baryons you would expect from the cosmic fraction. And so, okay, you've got two options. You either keep them out or you throw them out. And we know that it has to at least be a little bit of throwing them out, because if you look also at the metal fraction is not what you would expect from the population of stars that we see in galaxies. And these metals are, of course, made in the galaxies. So you can't simply reduce the metallicity of a galaxy by preventing it from accreting metals. Those metals were made inside. So we were kind of left with this situation at the beginning of my career where galaxies form at least twice as many stars as they should in our simulations. They couldn't form thin disks. They had too many dwarf satellites. Those dwarf satellites had the wrong dark matter density profiles, and everything had too many baryons and too many metals. And so, of course, the next step of the stereotypical talk is, we fixed it all. I've fixed it all. And of course, you'll know what's coming. So what's missing from this picture? The idea that the community is more or less settled on is feedback. We need that collapse to drive energy back into the system to resist further collapse and self-regulate. And both star formation and supermassive black hole accretion needs to be part of this picture. And it's a complicated picture. There are many, many different mechanisms that can dump energy into the interstellar medium. Some of them are driven by stars. This is where I've focused much of my work up until now. Others, though, are driven by that accretion process onto supermassive black holes. Some are complicated, scary MHD plasma effects that many of us are afraid to work on. But I'm really going to focus on these stellar feedback processes today and take a look at feedback driven by supernova, the deaths of massive stars, and feedback driven by stellar winds and ionizing radiation, sort of what we sometimes hear referred to in the field as early feedback that happens before the first massive star collapses. And so if you'll forgive me a moment, I've got teacher brain because I'm in the middle of the semester right now. So I'm going to do some back and forth here. Ballpark, what's the radius of the virial radius of the Milky Way? Anyone? 20?
Oh, virial radius.
Virial radius. 100, 200, ballpark, order of magnitude, great. Okay, what's the virial mass of the Milky Way? 10 to the 12. 10 to the 12 solar masses. It's got a stellar mass of about 5 by 10 to the 10. And so roughly the binding energy, twiddle a few constants here, is around 10 to the 59 ergs. Well, that's obviously significantly more than the energy released by a single supernova, but we get about one supernova per 100 solar masses of stars that formed. And so if we plug in these equations here, we see that there's at least enough energy available from supernova alone to completely unbind the Milky Way's halo. So this tells us two things. One, the obvious, there's enough energy there to do a lot of stuff. And so in other words, supernova could do almost anything, but because we actually see galaxies and they don't unbind themselves as soon as they start forming stars, we know that this supernova feedback cannot couple 100% efficiently to the mass within the galaxy. So we need to find this space between anything and nothing. And so obviously we're physicists, we're going to start looking at the physics. What's happening here? Well, when stars form, they tend to form, especially if they're massive, in these clusters. And so the physics is not really the physics of an individual supernova remnant, but of many supernova detonating in sort of a co-spatial and co-temporal environment, a superbubble, in other words. This superbubble pushes a shock into the ISM, and thermal conduction can move some energy back and forth. Other processes like turbulence can also be important here. And if thermoconduction is the thing that's dominating this mixing, then you end up setting up an evaporative mass loss where the mass in this hot bubble is set by its temperature and its surface area and this conduction coefficient. And so when you take this physics into account, you can kind of trace the life cycle of gas through a simulated galaxy. Gas from the sort of warm equilibrium, neutral and ionized medium will cool and form stars. Those stars will detonate as supernova, forming a superbubble, heating that gas to a sort of equilibrium temperature of a few million to 10 million degrees Kelvin. That will, of course, then leave the galaxy, and it will slowly evolve adiabatically through the CGM, where hopefully its cooling times are long. So in other words, the way to fix all of this is galactic outflows. And this has more or less been the conclusion of the field. Strong feedback, the advent of strong feedback about 10 years ago, really led to a renaissance of what we somewhat pompously started calling realistic galaxies. Galaxies with the correct stellar mass to halo mass relation across sort of a wide range of masses. And these are all coming from different groups too, which keep that in mind, keep that idea of diversity in mind. So one of the features of these winds that also was a nearly unanimous prediction of these many groups is that these outflows had to carry with them a lot of mass. In other words, the way it's working is you're just taking stuff out of the disk. So these mass loadings, in other words, where you look at the outflow rate divided by the star formation rate, which gives you a nice dimensionless number, were typically significantly higher than 1. You were throwing out more mass than you were forming in stars. And again, from different groups, different simulations, myself included, we were reporting that this seems to be a feature that we need. And all of this together can reduce your star formation rate. You're throwing out fuel. You can reduce the galactic baryon fraction. You're throwing those baryons out. And those baryons are going to drag some metals with them as well. And it turns out not only are you just getting rid of mass, you're getting rid of the right mass, at least it appears to be. So if you want to form a disk, you want high angular momentum gas. In other words, you want to remove the low JZ gas from the galaxy disk. And if we take a look at how these strong feedback models work, they're actually preferentially removing that low angular momentum gas that is forming your bulge while leaving more or less the same amount of high angular momentum gas to still allow you to form a disk. So these outflows also seem to remove low angular momentum baryons. And I won't dig into this in too much detail, but it seems also that this feedback can help fix your satellite population problems. You can end up getting much more reduced low mass satellites, fixing this missing dwarf problem, and also by heating the dark matter dynamically by sloshing the gas around, convert a cusp into a core. So we're great. We've solved it all. We might want to know, though, how these outflows evolve. And this is a big part of this picture. If it's the outflows that are doing this, knowing how these outflows work is going to be the key to knowing how the galaxy works. And so once again, we can ask ourselves, what is the physics at work here? If we take some Lagrangian fluid patch, a piece of the ISM that's been heated by feedback, what's it going to be doing? In other words, what's happening to it? Well, it's going to have energy and momentum injected into it by feedback. It's going to feel gravity pulling it back towards the center of the potential well. It's going to feel some hydrodynamic drag. The CGM is not empty. You can't simply launch something into it and not have it interact with the gas that's already there. And it's going to feel some radiative cooling potentially that's going to remove energy from it. And it turns out almost all of this physics can just be captured by looking at buoyancy, treating this problem as one of convection. And that buoyancy is going to determine whether or not that Lagrangian patch feels an upward acceleration or a downward acceleration, just through the standard Schwarzschild criterion that those of you who work in like stellar astrophysics are probably intimately familiar with. So if your entropy is higher than the entropy of your radius, you're going to feel an upward movement. If you have more entropy than your neighbors, they're going to push you up. And your entropy is just a function of your thermodynamic state, your temperature and your density. And if we look at the typical gas particle in one of these simulations and we calculate its radial velocity to split outflow from inflow, and then we plot that on average as a function of its entropy relative to the average entropy at the radius we find it, this is exactly what we see. Outflowing material on average has more entropy than its neighborhood, whereas inflowing material has less entropy than its neighborhood. And so the thing to do then, of course, is to derive some equations of motion. Again, we're physicists here, right? So the equation of motion governing one of these entropy-driven bubbles is one that really takes into account a couple simple terms. One is buoyancy. Is your entropy higher than the CGM entropy at the radius you find yourself? Gravity. Obviously, you're still going to feel a downward force from gravity itself, as well as hydrodynamic drag. And this, to all honesty, is the biggest uncertainty. So let's zoom in on the buoyancy picture. How do we calculate what the entropy of this hot gas is going to be? Well, it turns out if you turn the crank, use some of these classic analytic bubble solutions, you can derive an entropy for your bubble that depends on the ISM thickness. In other words, how big does the bubble get before it breaks out? The feedback power, what cluster is driving it, and the ambient gas density. The halo entropy then is just a function of your virial entropy. And if you're in hydrostatic equilibrium, you end up with this relationship. And the long and short of this idea is it gives you a totally different picture of how outflows evolve. If you're talking about outflows like baseballs or cannonballs that are simply thrown up with kinetic energy and then fall back after losing much of that kinetic energy due to drag, you end up with outflows that reaccrete in less than a gig a year and don't reach particularly high radii above the galaxy. Meanwhile, the same energy budget plugged into a buoyant outflow can give you outflows that take many gig years to reaccrete and reach a significant fraction of the halo's virial radius. So if the thing your outflow is supposed to do is keep that patch of material out of the disk, this seems to be the way in which you can do that efficiently. And the other thing that's nice about this is it gives you slow winds. Observationally, almost no cool clouds that are seen in these absorption line studies of the CGM actually have radial velocities above the escape velocity. We don't seem to be seeing material that is leaving the galaxy permanently. And in fact, many of these observations have velocities well below the sort of virial equilibrium velocity. And if we compare the average velocity to the average predicted buoyant velocity for halos of similar size, they're right on top of each other. This really seems to be the mechanism that nature is using. But of course, that question of how the breakout happens is really critical here. And a lot of good work has been done here at the CCI. I'm showing a figure from Matt's 2022 paper. And the question of what this cluster is going to do, is it going to produce a bubble that breaks out or a bubble that fragments, is a really important one. And so one of my PhD students, Javier Saavedra Moreno, is looking at kind of covering all of the angles of this question, and specifically the angle of what are the different ways in which a bubble can evolve towards breakout. So Matt's work really laid this foundation by starting from an assumption that you get a constant momentum per supernova that occurs. And if you relax that assumption and ask instead, okay, When a supernova goes off, you're going to have an energy-driven Weaver-like solution, and eventually it's either going to cool, and if it cools before the first supernova or before supernova shut off, you transition into this momentum-driven stage, and if it cools after, you have a brief Sedov-like period, and finally end up in this sort of momentum-conserving snowplow solution. And the interesting thing is, depending on how you assume this bubble is going to cool, you can end up in situations where outflows tend to be very, very common and hot. In other words, they are still in the period where supernova are detonating. And so you're dumping much of that energy straight into the CGM. So this is a paper that Javi is just on the verges of finishing. I'm hoping he'll get it out in the next couple of months. So keep an eye on the archive for this. So now we come to the next step. Nothing is true. I've just set up a problem and defeated that problem, and now I need to set up a harder problem because we've only been 22 minutes into the talk. So what do I mean by this? I've just shown you that there were these problems in our models of galaxy formation. They didn't agree with observations, but around 10 to 15 years ago, we started to develop a better understanding of how to build these simulations, the parts they need to contain, and how those parts have to work. And now those simulations agree, both with each other and with nature. But I'm here to tell you these simulations do not, in fact, agree. Not with each other, and therefore not with nature, because they can't disagree with each other and also disagree with nature. That would violate the commutative property of logic, I guess. And if you look at the CGM, for example, of different simulation projects, the fraction of the baryons within the galaxy that resides within that CGM is wildly different for different assumptions about how star formation and feedback work. If you look in even greater detail here at comparing, okay, where are the different pieces of your baryon budget between, say, for example, 3 large cosmological simulations? You'll notice that the stellar budgets are somewhat in agreement. That is because the stellar budget has been the thing we have been focusing on for decades, getting the stars right. But if you look at the hot gas, that is the gas within the CGM, none of these agree with each other. You could maybe argue TNG and Simba are somewhat similar in shape, but ultimately, these simulation projects are producing galaxies with similar stellar populations for 3 completely different reasons. In the case of Eagle, it has winds that completely blow out its CGM. It has very, very low baryon fractions. In the case of Simba, it's more or less preventing new accretion onto the CGM, whereas in the case of TNG, you are cycling material between the galaxy disk and the CGM and back again. All of these can produce galaxies with disks, with the correct stellar masses, with reasonable metallicities, but all of them are different physical pictures. And if we look at what these models are composed of course, there are the standard things we might worry about. Oh, are we matching resolutions? Is the box size the same? We're using different hydro solvers. I'd like to really focus in, though, on the stellar feedback question. So our field has really developed a cottage industry of feedback model builders, and I'm one of them. This was my first work as a PhD student, was developing one of these models. And over the years, we've been getting more and more and more of these models and more complicated models. And many of these models, take, for example, the one used in TNG here, have very, very many moving parts. These are essentially the free parameters in this model. And in order to sort of understand why these things are doing different things, we don't just have the question of how does the simulation map to reality. We really don't actually fully understand how the simulation itself works. On top of that, not only do these simulations not agree, no simulation result is exact. What do I mean by that? Well, there was a terrifying paper that came out in 2009 from some solar system simulators that simulated our solar system with a number of different realizations to look at potential outcomes. So they basically perturbed Mercury. That's the long and short of it. And in one of their high eccentricity solutions, a subsequent decrease in Mercury's eccentricity induces a transfer of angular momentum from the giant planets that destabilizes all of the terrestrial planets 3 gigayears from now with possible collisions of Mercury, Mars, or Venus with Earth. Cool, right? But what's terrifying about this is these perturbations in Mercury's orbit were differing its semi-major axis by 0.38 K millimeters, where K is a random integer between -1,000 and 1,000. So in other words, the difference between less than a meter in the position of Mercury today could be the difference between blowing up the Earth 3 gigayears from now and the solar system looking more or less the same. This is N-body chaos. We're all familiar with this, but N-body chaos is important to more than just protoplanetary or planetary systems. If you look at, say, for example, a simulation of pebble accretion, where in one case, you use a different initial random seed for placing your what should be identical disk, you end up with totally different solar system configurations. And so the question is, okay, if it matters for little disks, does it matter for big disks? And you can probably guess the answer is yes. Each of these column density maps is a simulation of the same initial condition run with the same code on the same computer with the same parameters. These should be identical. Nothing has varied here. And yet, you can see quite clearly a merger that is in the process of occurring in this case has not yet happened in this case. This is a universal effect. It's something that Shai and I kind of simultaneously discovered in 2019. It's also something that happens in isolated galaxies. If you look at the ratios of stellar masses formed between two different simulations of the same initial conditions with the same code, it happens in cosmological simulations. This is something that exists for all codes, for all subgrid models, and for all initial conditions. It's a real physical effect, or you might think of it as a mathematical effect. Because the fact of the matter is there is no correct seed for a random number generator. There is simply a seed. And to say that a simulation must perfectly reproduce a previous one is simply saying we're not going to choose to vary the things that don't have any real physical meaning, but actually impact the results. Luckily enough for us, we have self-regulating systems. So if you look at a galaxy simulated without feedback, you end up getting variations in stellar mass between two runs, massively larger than the Poisson noise shown here in the dotted line. However, if you turn on your self-regulating feedback, this noise or uncertainty approaches sort of the noise that you would expect just from the fact that you've discretized your stellar population. So you might think, okay, we're good, we're wonderful, we're all constrained to within this Poisson error here shown in the yellow lines. But the fact of the matter is not all galaxies stay self-regulated for their entire histories. A merger event that throws a galaxy out of equilibrium is going to take a while to settle down. And in that time, what turns out to be a very long time, multiple gigayears, you can produce variations in the stellar mass that is formed within that galaxy that are significantly higher than what you would expect just from this shot noise alone. And so this really leads me to my central thesis for this talk. This is from Nietzsche, Genealogy of Morality. It's nichts ist wahr, alles ist erlaubt. Nothing is true, everything is permitted. And so the question is this the case for us? Are we truly swimming in a void, or is there a way forward? And so I think part of this question is answered by rethinking what we mean by simulations. So the idea that a simulation is a mapping between an initial condition to a final state, much like a single mathematical function, and that we can compare two different models by simply starting from the same initial condition and then comparing the final state is just wrong. We're sampling a space here. It's a big space in many, many dimensions, perhaps an infinite dimensional space. But what we're doing when we're running two simulations with two different models is drawing one of many possible points from within the allowed space governed by that model. And so we might be able to say, okay, I've run a couple of simulations and they're different. I can compare them, but there may be these dangerous regions of overlap where the same model can potentially produce similar results and lead us astray. And so I think that it's more important to actually start to think about understanding the boundary of this region. So the shape of this space in configuration space. In other words, we're space explorers. The fact that everything is allowed for us means that everything we find that is true narrows down that possibility of what is allowed. And so we really need to not only be exploring observational space, doing deeper and wider surveys, we also need to couple that with exploring our model space, understanding how the model itself works while not really corresponding to empirical science is still an important step along the way. And finally, we have to understand the microphysics that go into our models. We're not necessarily assuming that you have a breakdown perfectly between something that is a subgrid model and something that is first principles, because many of the subgrid models take in assumptions that are coming from other parts of the field. And I'll talk about that in a moment. So let's start by exploring model space. So what do the models allow? I think what the way to think about understanding how we want to explore this is by looking at more and more of the things that are happening within our simulated galaxies. So let's look, for example, not at the stellar disk, but at stellar halos. So we know that stellar halos tend to be mostly ex situ, and they tend to be dominated by relatively older stars, and they live in the outskirts of the galaxy. Of course, these stellar halos are hard to observe. They have very low stellar masses, less than 10% of the galaxy's mass, and therefore they have terribly low surface brightnesses. So only recently has it become easy-ish to observe these things with new instruments like telephoto arrays. And so my friend Allison, pictured here, mapped a bunch of nearby stellar halos. And in opening up a new axis on this configuration space, detailed maps of resolved stellar halos, you can start comparing simulations. And in 2020, Allison found that illustrious TNG produced much more massive stellar halos than she was seeing in her observed dragonfly sample. So let's use this as a way to compare models. Let's take two different feedback models with the same initial conditions, one with this blast wave feedback that Daniel talked about earlier today, one with this newer superbubble feedback, and compare. And in fact, if we narrow our comparison down to ones that form roughly the same total stellar mass, we can start to really split degeneracies. We can ask, okay, if you form roughly the same total stellar mass, how about the mass that's just out there in the halo? And what we find is the feedback models can actually have a huge difference in your surface density of stars in the halo, especially in the outskirts here, more than a dex in change here, while still forming roughly the same amount of stars in total. And the reason for that, the reason we can now, in one of these cases, match a new observation, but not in the other case, is because we're changing where this regulation is happening. So in the one case with superbubble feedback, that supernova feedback is significantly stronger in halos with around 10 to the 9 to 10 to the 10 solar masses, which are specifically the halos that end up contributing most of the stars to the stellar halos around Milky Way-like galaxies. So new axes for comparing models can lead to new understanding. We can also compare what goes into these models. So let's think about supernova again. This is just a kind of survey of a couple of different simulations over the past 10 or 20 or so years. And you'll probably notice that, oh, this is a little scary. We've got a variation of a factor of 5 between the smallest amount of energy and the highest amount of energy injected per supernova. But we've also got wild disagreement in terms of when that supernova is injected. In other words, are we dumping this all at once? If we are dumping it all at once, are we dumping it when the star forms? Are we dumping it 10 years later? Are we dumping 10 mega years later, 30 mega years later? Or are we dumping it at a constant rate? Or are we matching some sort of functional fit for stellar lifetimes? Well, obviously some real physics sets this budget, the stellar physics that determines what progenitor masses detonate. Turns out this depends not just on the structure of the star itself, but whether it's got a neighbor, as well as your star formation physics. How many massive stars do you form? What's your IMF, in other words? So if we go back here, we've got a lot of physics that feed into these things that, for the most part, we as simulators have been ignoring or assuming is not important enough to look at. But let's look at the one that might be the least important, you'd think. Obviously, more energy is going to do more stuff, but maybe it doesn't really matter all that much about when that energy comes in. Of course, the answer to that is it does matter quite a bit. If you look at the same galaxy simulated where you dump the feedback instantaneously at star formation versus one where you wait 30 mega years, you can see obviously the gas morphology is different here. And the reason for this is it ends up changing your clustering. So the longer you wait for star formation, the more clustered that star formation is going to be. The cloud's not getting disrupted and it's continuing to form stars for longer and longer and longer. And we know that clustered supernova are more effective than diffuse supernova at driving outflows. And so this increased clustering leads to an increase in the outflow rate. And so phenomenologically, this microphysics effect that's going into our model, it has nothing to do with how the model's designed, it's really just a parameter, can end up having a order 50% change in the total stellar mass that's formed in an isolated Milky Way like galaxy over about 1 or 2 rotations. And so by exploring this side of things, we're learning something new about a different aspect, the clustering behavior. Now, this stellar evolution question is something really interesting because one assumption that we make that only recently has started to be explored is the idea that all supernova detonate with the same energy and that all massive stars above, say, 8 solar masses or so die as supernova. This is almost certainly not true. And as a result of including this variability in your supernova budget, you can once again very significantly change the star formation rate in a simulated galaxy, but we're not sure exactly what direction this goes. And so really we need to be able to explore this microphysics space easier. And this is a project that I'm working on now to basically develop a new population synthesis tool specifically to allow simulators to explore the parameter space allowed by stellar evolution models to all of the yields and things, energy, mass, metals, et cetera, that they care about to plug into their simulation code. So this is a project I'm working on with Marta Reina Campos, Lachlan Lancaster, my PhD student, Zach, Claude Cloutier, and Cloutier. Oh, Cloutier. My French pronunciation is awful. I'm from the western part of Canada. And Eric Anderson, not last but not least. And so exploring the microphysics side of things is going to get a lot easier once we've started to kind of compile what's out there. In other words, what is allowed. And finally, new observations will tell us about what is allowed in yet further dimensions of this configuration space. We've all seen the little red dots. And we've all seen the big scary doom and gloom statements about the first high redshift galaxies that JWST was seeing around redshift 10, that, oh my God, these early photometric surveys are showing galaxies with more stars than they should have baryons. It's a catastrophe. And all of the publicists were sending out press releases and writing articles about how, you know what, every cosmologist is probably going home and looking like this. But of course, this is not as simple as this. We know that photometric detections are tricky and that there's uncertainties in both the redshifts and in the stellar masses that form. But of course, spectroscopy was soon to come later, and we've had with JADES in December of 2022, the first sort of confirmed galaxies with spectra above redshift 10. And this was still kind of more or less reported as surprising. Well, we have many, many large volume simulations that have existed for years. You can see the earliest one published in this sample here is using relatively old cosmology, but these are all 10-year-old simulations, except for some of the more recent examples here. These have snapshots at redshift above 10, so we should be able to do some statistics here, but there was no observations to compare to. So obviously in 2015, to write a paper about what galaxy populations at redshift 13 look like wouldn't have been particularly useful, given that we had 10 years before there would be any observations to compare to. So these galaxies, that at least the ones JADES first found, have been in these simulations all along. If we look at the stellar mass of galaxies above 10 to the 7 in M star as a function of redshift, the JADES results are these white stars here, and all of our simulations are these various dots, the biggest dot corresponding to the most massive system in the volume. So every single one of these simulated volumes has galaxies with M stars above 10 to the 8 since redshift 10 or so. And many of them even have galaxies with 10 times as many stars within them. Now, you might be thinking, okay, these are very low resolution simulations. You're resolving these things with only a few thousand particles or so. Maybe this is just bad resolution. Well, we're definitely agreeing in terms of the star formation rate as well with these early galaxies. And if you look at sort of high resolution simulations, this is some work that's been done by Joe McCaffrey and John Wise. These are simulations zooming in on individual galaxies running at much, much higher resolution than I did. They're right on top of each other as well. The JADES results are here shown in stars. The simulations from McCaffrey's group are in the orange here, and the simulations I compared to are the blue. They're all following the same trend. And so these two access for us new dimensions. In this case, that new dimension didn't tell us the thing we hoped, that lambda CDM was broken and we had to rewrite everything. But every time we come up with a new metric, a new thing to look at, that opportunity is there. So I want to leave you with a couple of conclusions that are vaguish. Stellar feedback, I think at this point, is almost certainly going to be a required piece of galaxy formation. But the parameter space of what that feedback looks like and how it works is vast, and we have lots to still explore. Galactic winds may be the mechanism that feedback uses to regulate star formation, regulate the baryon content of galaxies, shape their dynamics. And I would argue that one of the best ways you can do that is through a buoyant process with entropy-driven winds. And finally, stellar clustering is a really thorny thing to think about in this particular case, because it is very easy to do changes that you would not expect to your models that end up changing the clustering, that end up changing the feedback, that end up changing who knows what down the line. But I don't want to leave you with conclusions, because that would violate my whole idea, which is that the fact that we have this vast space of uncertainty to explore is actually wonderful. So let me leave you instead with conclusions. And specifically, I want us to leave here abandoning the idea of trying to find out what is true, and instead ask ourselves what is allowed, what is possible, because we will never find what is true. That's a fool's errand. And the idea that our goal as simulators or theorists is to build the perfect model that reproduces nature completely throws out all the joy of having the ability to explore this space, and also is not going to work. So let's ask ourselves instead questions about how exactly or inexactly does a simulation map initial to final conditions? We need error bars if we want to start talking about whether or not two results agree. We need to ask ourselves about whether or not we really need to be looking at more and better observations of quantities we've already studied, or do we need to look at new things that we never even thought to look at before? And we need to consider what bit of microphysics is going into our models and simulations that we assume is settled, and that we assume is either too insignificant to matter or doesn't really have much error bars on it, because it turns out that oftentimes there's a lot more uncertainty in those inputs than we otherwise would have thought. So I wish I could tell you we're done, but I'm glad that I can't, because the whole point of this is have fun exploring. Thank you.
All right, plenty of time for questions. And those of you in the conference room, we do see you, so feel free to just put your hand up if you have a question, and I'll be keeping an eye on the Zoom as well.
I'm curious because I'm a cosmologist. Get parameters and stuff like that. So we care about what's true usually. So if we don't care about what is true, then why do we simulate things to try to get the understanding of what microphysics that we should be implementing? Or it's not that you don't care; it's impossible.
Yeah, I think it's. I would say I'm being a bit provocative and hyperbolic by saying give up on the idea of true. What I really mean by that is give up on true as a infinitely small point in configuration space, because we'll never understand what nature is doing well enough to narrow that range down to zero. And if it's not a point in configuration space, it's instead a volume within configuration space. And that volume then defines what is allowed, what is possible in our models. So the sort of way forward I see it is that we need to think much more clearly about, we're not trying to fit new simulations to new observations. We're trying to think about, this observation has shown us a new scaling relation. Let's say it's 1999 and I'm Rob Kennicott and I've just done the Kennicott-Schmidt relation. The correct response to something like that, in my opinion, as a theorist, is not to try and tweak your simulations until you reproduce the Kennicott-Schmidt relation, but instead understand what parts of your simulation models, your star formation law, your cooling, your feedback, causes the shape of that relationship to change, and in what way. In other words, figure out how the different pieces interact to basically understand the model in the same way that you think about trying to understand nature itself.
You mentioned about the new observations and not trying to fix that, but if this might be a bit large of the question, but what would be your ideal next set of observation, what would, if you could,
Mhm.
what would be your next focus for observer to help the development and understanding of these models?
Okay, I guess I've got two answers for that. One, if I can ignore the laws of physics, and one, if I can't. If I can ignore the laws of physics, I think the most useful single set of observations we could get would be a total resolved census of the hot diffuse gas in the CGM around many, many different galaxies. Because right now, the majority of what we have is either fairly close to the disk or these pencil beam absorption studies that have huge uncertainties because we're only sampling a tiny piece of the CGM. So if we could see the hot stuff, which we think is the volume filling component, I think that that would massively, massively improve our understanding. And we can do that in some cases, just not in the like massive survey sense. I think that the question about like what can we do with observations limited to what is practical. I actually don't think it's new observations so much as new things to measure from potentially existing observations. So I've talked to a lot of you while I've been here about different kinds of projects that are both theoretical and observational. And many of these new things, say, for example, one of the conversations I had this morning was looking at bar formation in galaxies. Now, there's been some work on cosmological simulations looking at this, but it's been relatively limited by resolution effects. Trying to find the connections between things that you wouldn't necessarily, basically going beyond the first order physics. So the first order physics for bar formation is galactic dynamics. Well, that is in turn impacted by your star formation, your feedback, your accretion history, these kinds of things. I don't think that the goal of us should be, I have the same bar statistics as nature. I think the goal of theory is to say, if you want longer bars, X, Y, and Z produce longer bars. If you want faster bars, A, B, and C produce faster bars. That to me is a more valuable understanding. And I think it's more likely to sort of span the test of time. That being said, all of this is hard. All of this is work. None of us are going to do it all by ourselves. Yeah.
Ask a controversial question?
Please.
But like, so, there's some areas of science, like, we can predict, rock falling down an incline plane, et cetera. And then there's some areas we can't, like the daily weather, right? And we just give up. We say
Yeah.
there's no purpose. So like, with galaxy formation, I'm feeling like I'm getting from your talk a little bit more like predicting the daily weather and like when do you say it's in this category and has predictive power, and when you say let's just have fun and I'm totally being controversial, but
No, I mean, that's you're striking at the sort of philosophical heart of what I'm proposing here, is that the answer, I think, is somewhere in the middle. And that's a bit of a lazy cop-out, but I also think it's true. I think that there are elements that are going to be very, very hard to ever pin down. But we are dealing with physical systems with conservation laws. Like we know that the galaxy is not going to violate any of the basic conservation laws, and that limits the sort of configuration space. And that really is kind of what I'm saying with this question of what is allowed, is we're not predicting a number, we're predicting a range. And in every case, I think the thing we need to remember is that just because the simulation can give us numbers out to machine precision doesn't mean that's actually the prediction of the physics we've put in. And it's certainly not like something we're ever going to be able to compare to observations at that level of precision. So part of that is we don't know how chaotic or uncertain these things are until we start looking. So for example, the idea that, oh, you know what? The timing of when you inject supernova matters. That's a numerical choice. That's a model choice. and it does give you some uncertainty, but you don't know how large that is until you've run the experiments. And so again, the goal of sort of my idea where the field needs to go is that we're, again, not aiming for a point, we're trying to map a volume. And hopefully, over time, once we started to map that volume and get an understanding of it, the goal is then to shrink that volume.
Okay.
Let me build on your provocative analogy and say that perhaps Ben is proposing that we shouldn't be trying to predict the weather in detail, but rather the climate globally.
Mm-hmm.
I think that's the natural extension of your statement. We may not be able to predict any given galaxy in all detail, and Alpha Centauri is there and the sun is there, but can we predict the statistical properties of galaxies over time? Well,
Yeah.
just as I think we can do an astonishingly good job of this long-term climate, even if we can't predict whether it's going to rain tomorrow with 100% certainty, so we can do cosmology, I think is what you're arguing.
Yeah, and I'm glad you brought the climate in as an example there, because I think that the climate simulation community has grappled with a lot of these questions in a much more rigorous way.
It's not like they don't know who the artist is. Never heard of them.
Somebody needs to be muted.
Classical.
Okay, as I was saying, yeah, I think that they have really grappled with this for longer than we have as a field. And
Carl,
No, it's a
please
piano
mute.
and a violin, I believe. Let me go and look and see rather than guessing. So,
Unfortunately, I'm powerless.
Who's host?
I'm
Yeah, you can mute them.
in control of the. Okay, we're good.
okay, all right, yeah. So I think we should be ripping them off, quite frankly, and again, being overly provocative for no reason here. But there is a literature out there for dealing with many of these questions. And I think that it's worth plumbing the depths of what's already been done, but obviously it's not going to solve all of our problems, and we do need to develop new ways of dealing with these uncertainties ourselves as well.
They average their models.
Yeah, and in fact, that's something I'm thinking about quite a bit here is model ensembling. That is a really, really powerful technique for them. And I think we have enough examples now that we can just start doing it without having to run more simulations. I think that there could be some really interesting, yet undiscovered ideas in there. Yeah.
Nicholas?
Yeah, thanks for a great talk. I want to ask you about feedback parameters and different models that actually do not agree in the predictions for the loading factors. You kind of glossed over that at the very beginning. And do you have a sense of which physical parameters is causing a loading factor that is extremely steep with low mass, the ones that's flat, the ones in the models, and the connections is also to the kinematics of the Kuroka's problems?
Yeah. So there are definitely models out there that have explicit terms that vary the amount of energy based on some property that is measurable locally, that oftentimes ends up correlating with galaxy properties. So if you scale, for example, as Eagle does, the energy injected by supernova as a function of gas metallicity, there's a mass metallicity relationship in galaxies, which means you are effectively scaling your feedback energy as a function of the galaxy mass itself. For models that don't explicitly vary things like this, I think it's a combination of the hydrodynamics, both the real stuff that we're trying to model and the numerical stuff that we're trying to avoid. I think one of the reasons, for example, that these highly mass loaded winds have been a popular solution in the field is when your ISM is relatively coarsely resolved, you're effectively simulating a more viscous fluid than you ought to be. And if you've ever tried to boil molasses, rather than simple little bubbles that pop out like a pot of water, the entire thing will rise and then fall and rise and fall. And so I think we may be dragging more material out in our winds simply as a function of resolution. But of course, more resolution is expensive, and many of the approaches that are getting to be popular now are really essentially trying to avoid that problem altogether by keeping your cool component as some sort of subgrid set of clouds. A lot of that work is being done here, and I think that may be one of the only ways forward here.
Bullet 3. Magnetic fields depend on the mass of the galaxy. Cosmic ray diffusion depends on the strength of the magnetic field.
Yes. Yeah, well, I mean, in my introduction there, I disappeared the cosmic ray slide pretty quickly because I neither have much work to present on that nor much insight into the physics of it either. But I definitely think it's another piece, it's another axis in this horribly high dimensional space. Yeah.
Okay, I propose